Hello everyone, beginning with biomechanics basics. Biomechanics. It is the study of application of mechanical forces to living organism. It includes forces that arise from within or outside the body. So the biological cascade of events that ultimately results in bone remodeling and the orthodontic tooth movement, it begins with the mechanical activation of an orthodontic appliance. Orthodontic appliances obey the laws of physics and can be activated to generate the desired force systems to achieve predetermined treatment goals for individual patients. So, understanding the biomechanical principles underlying orthodontic appliance activations is essential for executing efficient and successful orthodontic treatment. In orthodontics, it refers to the application of mechanics to the biology of tooth movement. Orthodontic therapy depends upon the reaction of the teeth and more generally the facial structures to gentle but persistent force. So force is applied to the tooth through a variety of appliances. Understanding the biomechanics is essential to determine the working of an appliance and more importantly the undesirable changes associated with it. Now coming on to force. So force, it is the agency that tends to change the momentum of a body, or it is an act upon a body that changes or tends to change the state of rest or the motion of that body. So force is given by mass into acceleration. So acceleration is nothing but it denotes two things, magnitude and direction. So magnitude and direction and point of application must be taken into account. Force vectors are represented as arrows. So the length of the arrow is proportional to the magnitude of the force. So the actual length is arbitrary and will vary with each particular diagram. Uh, then orthodontic forces can be treated mathematically as vectors. When more than one force is applied to a tooth, the force can be combined to determine a single overall resultant. So forces can be divided into components in order to determine effects parallel and perpendicular to the occlusal plane, frontward horizontal or the long axis of the tooth. So when forces are provided along the long axis of the tooth, it can either be a pull force or a push force. So a push force will denote intrusion, a pull force will denote extrusion. So similarly in the sagittal direction, it can either be retraction or protraction. Now, the tendency of or the tendency to rotate is due to the moment of the force, which is equal to the force magnitude multiplied by the perpendicular distance of the line of action to the center of resistance. So, the only force system that can produce poor rotation is a couple, which is two equal and opposite non-collinear but parallel forces. So, the movement of a tooth can be described through the use of a center of rotation. We will be discussing all of this in the subsequent slides. So, as I mentioned, the arrow signifies the direction of the force and the length of the arrow signifies the magnitude of the force. Magnitude is nothing but the power of the force, or it is a quantification. Now coming to rigid bodies. So a rigid body is by definition one that may be assumed not to change its shape under the influence of forces. For this reason, teeth may be considered rigid bodies. So forces that tend to pull apart by elongation are called tensile forces, and that tend to compress the body by shortening it are called as compressive forces. So one might note that in both tension and compression, the forces are acting in the same direction along the long axis of the tooth. But one is a plus and the other is a minus. Imagine we give a force in this direction. So here there is compressive force on the palatal side of the tooth and there is a tensile force that is rendered on the labial side of the tooth. Coming on to mass and weight. So mass applies to every particle of matter in the universe. So the mass of any body is the quantity of matter it contains. An upper permanent first molar, for example, has a greater mass than a lower central incisor, and it also weighs more. And one can measure the quantity of mass these teeth contain by weighing them, since mass and weight are proportional but not same. Now coming to center of mass. So the center of mass of a body or system of a particle is defined as a point at which the whole of the mass or the whole of the mass of the body or all the masses of a system of a particle appear to be concentrated. So in physics, we can say that the center of mass is a point at the center of distribution of mass in space. So this is also known as uh, balance point, wherein the weighted relative position of the distributed mass has a sum of 0. So technically in the center of mass, uh, because of the distributed mass, the sum is equal to 0. So in orthodontics, we call the center of mass as center of resistance. So the point of force application needed to bring about a pure translational or bodily movement of an object is called as center of resistance. So imagine we have the center of resistance of this door is in the center. So when this person pushes along the uh, axis passing through the center of resistance, there is pure translational movement or bodily movement of the door that takes place. There is no change in the angulation of the door as such. So this is a pure bodily movement. Now coming on to moment. So measure of the tendency to rotate an object around some point. So moment is generated by a force acting at a distance. So quantitatively, it is the product of force times the perpendicular distance from the point of application of force to the center of resistance. And this and thus is measured in units of gram millimeters. So if the line of action of an applied force does not pass through the center of resistance, so a moment is necessarily created. Not only will the force tend to translate the object, moving it to a different position, but it also will tend to rotate the object around the center of resistance. Thus, um, precisely in the situation when a force is applied to the crown of a tooth, not only the tooth is displaced in the direction of the force, but it also rotates along the center of center of resistance of the teeth. Thus the tooth tips as it moves. So imagine this is a tooth and this is the center of the resistance. So we, as already mentioned, when a force is uh, provided along the axis passing through the center of resistance, there is a bodily movement that happens. But when a force is rendered uh, away from the center of resistance, then this is the point of application of force, and this is the perpendicular distance. So perpendicular distance that joins the point of application, the line passing through the point of application of force and the center of resistance and the perpendicular distance. So momentum will be force into displacement. Imagine a force of 1 Newton is provided uh, through a distance of 2d. Then the moment cost will be 2. Coming on to couple. So couple is a two force system. So in couple there is no displacement or bodily movement that takes place, but it is a pure rotational force. So here two forces are provided in the opposite direction. So and when two forces are acting in the opposite direction, as there will also a moment is created which will lead to a pure rotation of the system. So this two couple system can be used in correction of rotated teeth. Now coming on to center of rotation. So center of rotation is a fixed point around which a two-dimensional figure is rotated. So it is the point that remains stationary during the rotation of that particular figure. So for a teeth, the center of resistance and center of rotation need not be the same. So here, when a force F is provided, the center of rotation, which lies at the junction of the apical and middle third of the root. So when this force is provided, there is merely a rotation of the tooth that is taking place, and this point remains fixed. That is, the center of resistance, there is a path that is taken by the center of resistance, but the center of rotation remains stationary. These are the different moment to force ratios. So in pure tipping, the moment to force ratio is less than 1. In control tipping, the moment to force ratio is 1 to 7. And in bodily movement, it is 8 to 10. And in torque, where only we expect only the force to be expressed in the root, the torque is more than 10. Coming on to equivalent force systems. So an equivalent force system is one in which where we are applying force to the teeth or any system, and it is a simple force system, so in which the forces can be reduced and still produce external effect on the body. For example, if someone pushes a person on the left side with million-pound of force, another person does the same on the other side, the person will not move at all. So when we are applying force to the teeth, it is impractical to place the forces at the center of resistance as it requires high pain threshold. However, an equivalent force system can be placed on the tooth. So force systems at the serous is system 1 and at the tooth is system 2. So consider a 100 grams of force is applied at the level of the bracket with the help of certain appliances. So this is force system 1. Imagine the same force being applied at the serous but also with a moment. So this is called a force system 2. So a single force at the crown is equivalent to force and a moment at the serous, and the tooth will rotate in a mesiodistal direction. So the measure of this tendency to rotate is called the moment of force. So magnitude of moment is force into perpendicular distance between its line of the action and point at which the rotation is considered. So positive moments tend to rotate such that the mesial surface rotates lingually, and the negative moment is such that it rotates buccally. So now coming on to types of tooth movement. First, tipping. Uh, so for any tooth movement, identifying the serous is a very important step. So what is uncontrolled tipping or an excessive tipping? So movement of the tooth about a serous and very close to the serous. So crown goes in one direction whereas the root goes in the opposite direction. It could occur in any view. So here the serot is very close to serous and maximum stress at PDL, root apex and alveolar crest is observed, and it may also lead to labial bone fenestration. And in control tipping, the center of rotation is at the apex of the tooth. This involves a moment and a force, and the tooth tips about the serot. For example, in correction of class 2 Devon malocclusion with maxillary anterior proclination, the use of uncontrolled tipping could lead to perforation of the buccal plate, whereas a controlled tipping will result in the movement of only the crown. So the root will not perforate the buccal bony plate. So this is an example of controlled tipping. So it can be used in class 2 div 1 cases, and uncontrolled tipping can be used in class 2 div 2 cases where we also require the movement of the root. in class 2 div 2 cases, the roots are placed labially. So when uncontrolled tipping is done in class 2 div 2 cases, the roots move lingually and the crowns move labially. Now moving on to the next, the translation or bodily movement. So as I already mentioned, it occurs when C rot is located at infinity. So every point on the tooth, it moves in parallel line in the direction of the force. So there is no uh, uh, path, or there is no circular path that is taken by the tooth. So this C rot is at infinity. So translation results in bodily displacement. So this can be used when we are retracting the teeth. Now coming on to intrusion and extrusion. Intrusion and extrusion involve movement along the long axis of the tooth. So the center of rotation is at infinity. The center of rotation is at infinity in this type of movement because there is no rotation that is happening. So in other words, the tooth is rotating about a point that is at infinite distance away, such that we do not see any rotation, just a translation, or it's just a translation in the vertical axis. That is the intrusion or extrusion movement. So the fall in coming on to root movement. So root movement occurs when the center of rotation is at or near the incisal edge, and the rotation occurs about this point. So the crown therefore is displaced less than the root. The root movement takes more time because the bone resorption required for the movement to occur is more. So here the crown of the tooth is stationary, and we expect only the root torque to be expressed. So coming on to rotation. So pure rotation, as I already mentioned, requires a couple force. No net force acts at the series, so only rotation occurs. This movement is required for derotation of teeth. Now coming on to moment to force ratio. So control tooth movement, having control of the centers of rotation of teeth involved. So the forces are prescribed in correct amount in order to achieve desired tooth movement. So the moment to force ratio at the CRS determines the stress pattern in the PDL. In other words, how a segment of a rigidly connected teeth will move. By controlling the moment to force ratio at CRS, one can produce different stress levels in PDL, and different centers of rotation. So the moment of force ratio combines the translational and rotational moments. The ratio is determined by the amplitude of force multiplied by the perpendicular distance um, of a tooth or a group of teeth. So by changing the moment to force ratio, different centers of rotation can be produced. So if a moment to force ratio is decreased, that is when M is made constant and force is increased, then you get more of translational um, moment, because the center of rotation goes towards the apex of the tooth. So if the moment of force ratio is increased by increasing the momentum moment, or decreasing the force, there will be more rotation, since the center of rotation will move towards the center of resistance. Coming on to static equilibrium. So it is an application of Newton's law of motion to the analysis of the force system delivered by an orthodontic appliance. So when orthodontic appliances are activated and inserted, tooth movement does not occur immediately, but it proceeds slowly over an extended period of time. So for this reason, the physical laws of statics are considered adequate to describe the instantaneous force system produced by orthodontic appliances. The physical laws of statics are governed by Newton's third law of motion, which is, for every action there is an equal and opposite reaction. So in the state of equilibrium, the summation of horizontal forces, vertical forces, and transfer forces are used 0, and also the summation of moments in horizontal, vertical, and transverse axes are also 0. So the orthodontic system ultimately comes to a state of static equilibrium from a dynamic state resulting in zero forces and moments across the system. So the orthodontic application is that for every appliance, but necessarily for every tooth to which the appliance is attached, the sum of forces and moments must be equal to 0. That is, they must be present in a static equilibrium. Type of force systems. So the laws of equilibrium require not only that for every force there is an equivalent opposite reactive force, but also that the sum of the moments around any arbitrary point is equal to 0. In other words, the moments as well as the forces generated by an orthodontic system must be balanced in all three planes of system. Now, there are two different types of systems. So, they are statically determined, meaning that the moments and forces can readily be discerned, measured, and evaluated, or as indeterminate. So, statically indeterminate systems are too complex for precisely calculating all forces and moments involved in the equilibrium. So, typically, only the direction of net moments and approximate net force levels can be determined. Determinate force systems, therefore, are particularly advantageous in orthodontics when control of force magnitudes is necessary to produce the desired biological response. For all practical purposes, determinant systems in orthodontics are those in which a couple is created at one end of an attachment with only a force at the other end. So, when there is no force on the other end, it's called as a one couple system. So, this means that a wire that will serve as a spring can be inserted into a tube or a bracket at one end, but must be tied so that there is only one point of contact on the other. When the wire is tied into a bracket on both the ends, a statically indeterminate two couple system has been created. So in orthodontic applications, one couple systems are found when two conditions are met. So a cantilever spring or auxiliary arch wire is placed into a bracket or tube and typically attaches to a teeth or tooth that are part of a stabilized segment. The other end of the cantilever spring or auxiliary arch wire is tied to a tooth or a group of teeth that are to be moved with a single point of force application. So for analysis, the teeth in the anchor unit are considered as if stabilization had created a single large multi-rooted tooth with a single center of resistance. So it is important to tie teeth in an anchor unit tightly together with as a rigid stabilizing wire segment as possible. So often the posterior teeth on both sides are tied together with a rigid lingual and palatal arch so that a posterior stabilizing segment is created. So if the goal is to move more than one tooth, the tooth movement segment similarly must be tied so that the teeth become a single unit. Coming on to two couple systems, so these are those which are inserted into the tubes or bracket on both ends creating couples. So a couple therefore may be generated by the wire at either or both the attachment sides. The force systems produced by two couple appliances depend upon the wire geometry and bracket angulation relationships. We hope you have understood the concepts of the basic biomechanics that was discussed in this PPT. Stay tuned for future uploads.